Tall, slender structures like this are susceptible to wind-induced vibrations. Anyone that has seen lampposts shaking in the wind will have seen this in action. So what's happening here? Let's place a cylinder in a wind tunnel and examine what happens as we increase the air velocity. In a steady flow of air, you would assume that the net force on a cylinder would be in the same direction, like this, and you'd be right. At lower speeds this is the case. Here the light bulb would just bend in that direction, and while the wind speed and direction may fluctuate, you wouldn't see these consistent back and forth vibrations. As we increase the speed, the air begins to separate from the surface of the cylinder, creating two symmetrical eddies behind the cylinder. Eddies are regions of slow-moving, swirling fluid. You'll see these a lot in rivers where branches or bridge pillars block the flow. Here is one in my hometown of Galway. Kayakers use these eddies when they need to rest from the fast-moving mainstream. If we keep increasing the fluid velocity, these eddies will grow, and the force on the cylinder will also grow. But as long as these eddies are symmetrical, the force will remain in the direction of the fluid flow. But there is a critical moment where the system loses its stability. The energy gradient from the mainstream and the slow-moving eddies becomes too high, and eddies begin to oscillate. At this point, a phenomenon called Vortex Shedding occurs, and the resultant force is no longer directly downstream. It teeters between the alternating low-pressure zones as the vortices are shed on either side of the cylinder. This can become a massive issue if the frequency of the shedding matches the resonant frequency of the structure. That means that the direction of sway and the direction of the force become synchronized, and the amplitude of the swaying is allowed to grow as energy is being stored between each cycle. Every building dissipates some of that oscillation energy through natural damping.